Hello dear DP and other physics students. Welcome back to Rubber Duck Physics. In video number 2, we saw how the Michelson-Morley experiment showed that the speed of light seemed absolute, contradicting what we would expect from Galilean relativity. In video number 3, we introduced the Lorentz transformations, which solve this paradox mathematically. But why should space and time behave this way? We need a new starting point, something fundamental that doesn't rely on old assumptions. Einstein provided exactly that, with his two postulates of special relativity. We saw in video number 1 that Galilean relativity says the laws of mechanics are the same in all inertial frames. But what about other laws of physics, like electromagnetism, light, waves, and so on? If Galilean relativity only worked for mechanics, it would create an inconsistency in how nature operates. Would physics be split into different sets of rules, one set of them for mechanics, another for electromagnetism? That wouldn't make sense. To fix this, Einstein did not try to derive a new theory. Instead, he started with two fundamental principles, postulates, that would define the structure of special relativity. Postulates are a small number of fundamental statements which a theoretical scientist, or a team of them, does not aim to prove. Instead, they conditionally accept them and they see them verified if they can build a consistent, robust theory upon them, which, when tested, matches experimental evidence. Einstein's first postulate states that all laws of physics, or more precisely of nature, are the same in all inertial reference frames. This means that no experiment, mechanical, electrical, or any other, can tell you whether you are moving at constant velocity or standing still. In video number 1, we saw how Galilean relativity worked for mechanics. Einstein extended this idea to all of physics. Imagine you are inside a sealed spaceship floating in space stationary, with no windows. You throw a ball, shine a flashlight, and check a magnet's behavior. Everything works as expected. Now, suppose the spaceship is moving at constant velocity. According to Einstein, every experiment inside the ship will give identical results, because the laws of physics don't change with motion. There is no absolute frame of reference. This is the principle of relativity. But now let's introduce the second postulate, which is even stranger. Einstein's second postulate states that the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This is where things get counterintuitive. In video number 2, we saw how the Michelson-Morley experiment proved that light's speed didn't change with Earth's motion through space. But this result clashes with what we expect from classical physics. If you throw a ball forward on a moving train, it moves faster than if you threw it while standing still on the railway platform. So, if a spaceship shines a beam of light forward, shouldn't a faster spaceship see the beam traveling even faster? No. According to Einstein, both ships will measure the exact same speed of light. Imagine two ducks in space. The yellow duck is floating motionless, and the blue duck is moving at half of the speed of light. Now, both ducks shine a flashlight forward. According to classical physics, the blue duck should measure a different speed of light than the yellow duck. But according to Einstein, both ducks measure the speed of light as exactly the same, 300,000 kilometers per second. If these two postulates are true, then the consequences must be radical. For light's speed to remain the same for all observers, space and time must be different for moving observers. If one observer sees a light beam travel one distance in a certain time, but another moving observer sees it travel a different distance in the same time, how can both measure the same speed? The answer is that time and space must adjust. We'll expand this idea in the next two videos, number 5 and 6. But before we go, let's look at how velocity must be transformed in relativity. In Galilean relativity, we transform velocities with a simple equation u dash equals u minus v. But this equation contradicts the second postulate. If we use it for light, different observers would measure different speeds, which Einstein says cannot happen. Instead, relativity uses the Lorentz velocity transformation, which we have met in the previous video, number 3, and it correctly predicts that light's speed is always c. The relativistic velocity transformation is u dash equals u minus v divided by 1 minus u times v divided by c squared. With this equation, if u equals c, then u dash also equals c, meaning that the speed of light remains constant in all frames. This confirms that Einstein's postulates are built into the mathematics of relativity. These are the two postulates of special relativity. They were, when accepted as the starting point, sufficient to develop the whole theory. Let's quickly summarize what we have learned. Einstein's first postulate says that the laws of physics are the same in all inertial frames, not just mechanics, but all laws of nature. His second postulate says that the speed of light is always the same, no matter how fast the observer or the source is moving. These postulates force us to rethink space and time and explain why we need the Lorentz velocity transformation instead of the Galilean one. Before we wrap up, let's consider something strange. Imagine two astronauts are moving relative to each other, both carrying identical clocks. Since motion affects time, could one astronaut's clock tick slower than the others? But if the laws of physics are the same for both of them, how do we decide which one is experiencing slower time? This is a paradox, and the answer lies in one of the most famous consequences of reality, time dilation, which we'll explore in the next video, number 5. Before we go, remember that I'm available to tutor physics and math students. If you would consider some one-to-one online help with high school physics or mathematics, I'd be happy to hear from you. You can find my email address in the channel data of the Rubber Duck Physics YouTube channel. It's visible only if you are using a browser on a computer, not in the app. Feel free to reach out and let's see if I can help you. Thank you for watching Rubber Duck Physics. See you next time.